very pleased to introduce today's Colloquium speaker, Professor DeMarco. She's from Northwestern University and she's visiting IMS here. So she will talk about complex dynamics and elliptic curves.
Thank you very much. So the goal of my talk is to explain. Wait.
Oh, more. Maybe somebody. Yes, yes.
Everybody loves you. I think we're good.
Okay, so as I was saying, the goal of the talk is to explain some connections between two different subjects. I've described here complex dynamics and elliptic curves, but another goal of the talk is to explain what this is a picture of. So maybe by the end of the lecture, I'll show more pictures and try to describe what they are. So this beautiful picture with lots of dots has a meaning, and I'd like you to know what that meaning is. So the two subjects that I want to relate today are these. So on one side, we have complex or algebraic dynamical systems. And on the other side, arithmetic geometry. So I've tried to describe in a nutshell what these are as mathematical subjects. So on this side, so by dynamical system, I mean that I have some sort of space X, or a set, and a map from X to X. And in dynamics, what do we want to do? At least at the level of points, we want to study orbits. So I have a discrete dynamical system, so a map from X to itself, and I want to study starting with any point X. I want to study the sequence of points, which is defined in this way, where you take a point and you apply F, and you apply F again, and you apply F repeatedly. You have this infinite sequence of points that and you want to understand where it is in the space. Now what makes it complex or algebraic dynamics is that the space itself is endowed with some extra structure. Maybe it's an algebraic variety, a complex manifold. And then we'd like the map to respect that structure. So F is some morphism in this vocabulary that we're working with. On the other side, we have arithmetic geometry. So maybe the space is the same. We're interested in perhaps the same object, but not viewed as a complex algebraic variety, but maybe defined over some field K, where K is not algebraically closed. And maybe we're interested, again, at the level of points, to look at the collection of what are called rational points. So if an algebraic variety is a set of solutions to some polynomial equations with coefficients in your given field, then this is the notation for the set of solutions which also lie in the given field, X of K. So this is just to give a parallel. What are the subjects? And I'd like to explain how the dynamics comes in, how the geometry plays a role to combine these two things. And for this talk, I will be as concrete as I can and talk only about one particular setting, where X is the simplest possible complex algebraic variety here, namely the Riemann sphere. So throughout the talk now, I'm just thinking of maps from the Riemann sphere to itself, so P1 over C, or in other words, just C together with infinity. And what are the maps, the morphisms in this setting from X to X? These are just rational functions. So F is just a ratio of polynomials, and its coefficients are complex numbers. Now, in the study of dynamical systems, one of the things that's well known is that as soon as F is not invertible, so if F is invertible, it's a Mobius transformation. And from a dynamical point of view, they're not very interesting to look at just one Mobius transformation. But as soon as F has degree bigger than 1, so it's not invertible, then we get these beautiful pictures of Julia sets. We have chaotic dynamics on the sphere. And so this is just an illustration of one Julia set for a particular degree 2 rational function that I chose because I liked the picture. But I won't define Julia set because it doesn't matter for the sake of this talk, its definition, but one thing to emphasize is that the coloring in this picture represents orbit behavior. A pixel is colored pink if that orbit is doing something particular. A pixel is colored yellow if its orbit is doing something different, and the shading represents the different kinds of orbit behavior. So we get beautiful pictures of this sort. But to connect it to the arithmetic geometry, there's a very special class of such maps that come from elliptic curves. Okay, so on the right-hand side here, I have a picture of a complex torus, or an elliptic curve, if I think of it with its group structure, and a particular point which represents the 0 in the group. Now we know that the quotient of an elliptic curve, if you glue a point to its additive inverse, the quotient is topologically a sphere, and you get the Riemann sphere with its complex structure. So the elliptic curve here projects down to the Riemann sphere. And what is the special class of dynamical systems I'm interested in? Well, if you take any endomorphism of this elliptic curve, then it will descend by this quotient to now a morphism, or a rational function, down on P1. Now, from a dynamical point of view, I guess these objects have been studied for many, many years. So I guess actually more than 100 years. Here are two names that I guess were early contributors to the study of the dynamical features of this particular quotient. But I guess from the point of view of understanding Julia sets or the chaotic dynamics, you don't get very interesting pictures. If you take one of these examples and you try to draw the corresponding picture, just for fun, you see something like this, meaning you see nothing in the sense that the Julia set for any of these examples is actually the entire Riemann sphere. So you don't get beautiful pictures from these examples, but that's not why they're important. So I want to emphasize really why I'm talking about them. So this paragraph here is to illustrate a very elementary but very important relation between the algebra upstairs and the dynamics downstairs.
Are you always assuming that phi is invariant under the Weierstrass equation?
Well, I'm taking an endomorphism. I'm taking, so it's respecting, so it's a homomorphism here. So I am assuming that it does respect the quotient here. Yeah. And so just to take an explicit example, for example, if I take the endomorphism, which is p goes to p plus p, or in other words, multiplication by 2. This is just a reminder and a definition. So just remember that a point is torsion in the group structure if you add it to itself repeatedly and you get the 0 element. So again, to relate the algebra upstairs to the dynamics downstairs, just from the definitions, you can see that a point on the elliptic curve is a torsion point if and only if, under repeated multiplication by 2, the point is pre-periodic, or in other words, its orbit will be finite. As you repeatedly apply multiplication by 2, if it's torsion, you're just taking the powers of 2 times p, and this is a finite list. So eventually this has to repeat. Okay? But if you take that statement and project it down here, that's the same thing as saying that the projection has a finite orbit for this particular chaotic dynamical system. Okay, so it's just, and this just follows from the definitions, and it's an if and only if statement, that torsion on the elliptic curve is equivalent to a dynamical statement pre-periodic on the Riemann sphere. Okay, so it's just from the definitions. But this little or elementary relation between the algebra and the dynamics plays a role in many, many statements throughout history, and I want to present a few of them and some of the recent ways in which it plays a role in history. Okay, so we have to try to keep that in mind again, that torsion on the elliptic curve is equivalent to pre-periodic for the corresponding dynamical system if you take any non-trivial, in this case endomorphism, in particular multiplication by 2. All right, so here's the first example where this phenomenon, this connection plays a role. This is the Mordell-Weil, classical Mordell-Weil theorem about elliptic curves. So what is the statement? If you take an elliptic curve defined over a number field, so here's an explicit example of one. So you take the solution set of this cubic equation, y squared equals this particular cubic. I just wrote one down. Doesn't matter, the 22 over 37. It was just an explicit example defined over the rational numbers. Let's assume it's defined over a number field, so maybe some finite extension of Q. And the theorem of Mordell in the case of Q and Weil in the case of number fields is that if you look at the set of solutions over K, the set of rational points on your elliptic curve, then this is a finitely generated subgroup, finitely generated group. So it's certainly a subgroup because the So the addition and the inverse operation will preserve rationality, but the key point here is the finite generation of this group. And so in particular, let's focus on the part that I'm trying to emphasize in the previous slide. So in particular, the set of torsion points is finite over when you fix this particular field. Of course, if you pass to the algebraic closure, then there are infinitely many torsion points on an elliptic curve. But if you restrict the field, there are only finitely many. Okay, so one of the ways in which this phenomenon, this finiteness, is explained, so the more modern language, slightly more modern than 1920s, so let's say 1960s, explanation of this finiteness goes as follows. So what a number theorist might look at is something called the Néron-Tate canonical height function. So there's a real valued function defined on these algebraic points of the elliptic curve. So it has a definition, I'll come back to it, but the key property here is that this function is somehow measuring some complexity of these points on the elliptic curve, and the torsion points are precisely the points of height 0. So the height is actually a non-negative value function, and the height 0 points are precisely the torsion points. And in the case of the number field, just formal height property, which is really what Weil had introduced in his work in the 1920s, and what's now called the Northwestern property, actually, of these heights, is that this is a finite set. If you restrict the field and bound the height, this set will be finite. So in particular, if you look at the rational torsion points on the elliptic curve, it's a finite set. It's a special feature of number fields. But two things on this slide I want to emphasize is that, well, again, so the height is, again, some measure of arithmetic complexity, which I'm not going to define formally right now, but I want to emphasize this ingredient here. So the way that Tate, in around 1960, constructed this particular height function, this what's now called the canonical height function, or Néron-Tate height function, is a dynamical construction. So what are these symbols here? So I'm starting with a point P, which is on the elliptic curve. This 2 to the n is multiplication by 2 repeatedly, or in other words, iteration of the endomorphism of 2 to the n. So this is a dynamical operation. Pi, from my previous slide, was the projection. So just to remind us, I had my elliptic curve, and I had some endomorphism, for example, P goes to 2 times P, and then pi was what I called my projection, where I'm gluing P to minus P. And then I have P1 down here, and then I had some map F at the bottom, which depends on the endomorphism, etc. So really what he's doing is he's looking at the height, which is really a height function defined down here on P1, and then you take the points, you project them down to P1, and then you look at the growth rate of the height. One expects these heights to grow exponentially as you multiply the point, and then it's this in fact what he does, is he looks at the growth rate of this height function. And that's how it's one of the ways that this height function is constructed. So it's a dynamical input. So, well, actually, one other interesting thing that I want to point out is that this finiteness at the end was, in fact, particular to number fields. And so if you change the field, if you work with a different kind of field here, then this theorem may or may not be true as stated. So I just want to say a little bit about what to do or how to fix this kind of argument in the case where it's not a number field and we don't have this finiteness property automatically. Well, I did have an explicit example, but let me just draw a picture instead of giving a formula. So the corresponding theorem for function fields, which was established a little bit later, is that if you start with an elliptic curve now defined over a function field, then its set of rational points, again, forms a finitely generated group, but under one additional hypothesis, namely, they have to assume that the elliptic curve is not isotrivial. And because I want to illustrate another connection to dynamical systems, I want to explain a little bit more about this statement before moving on to more modern theorems. Okay, so to explain a little bit more about this statement, so to have an elliptic curve over a function field, if you haven't thought about these things, so in complex geometry, the way you might think of it is, let's say the function field is this. If you fix a Riemann surface X, and the field is the field of meromorphic functions on X, that's what my little K is in this picture, and so an elliptic curve over this function field just means a family of complex tori, a family of elliptic curves over my base X. Okay, so I view this as a surface, a complex elliptic surface over X. And what does isotriviality mean? That just means that the fibers would not be varying. Their complex structure would all be the same. Of course, we know there's a one-parameter family of Mixtori, and so isotrivial would mean that they were all the same. They would all the fibers would be isomorphic over C. So, for example, it might be a product surface, the base crossed with one particular complex torus. And that would be bad for the Mordell-Weil theorem, the finiteness, because, I mean, what is a rational point? So just to remind you what that means, a rational point is just, in this case, a section, a holomorphic section from the base up into the surface. And if, for example, you have just a product, so if your surface here is just the base crossed with a fiber, then you have lots and lots and lots of rational points, because you could take any point in one of the fibers and just take the product, just take the horizontal slice through that point, and so you certainly get lots and lots of rational points, and you get infinitely many torsion points in particular. So isotriviality would clearly be a problem for such a finiteness, a finite generation statement. Okay? But it turns out that's the only thing that can go wrong. And let me again focus on the torsion points for a moment and give you a proof of the finiteness, but now using dynamics. So let me just show you a proof of the finiteness of the collection of torsion points on this elliptic curve over a function field using topology, actually, using iteration and topology. So, well, a sketch of the proof, really. I'm not going to use the full proof. So what do I do? So I just want to use exactly the same picture, again, the same elementary idea of connecting torsion points to the notion of finite orbit under a particular dynamical system. So let's, for each fiber, we can project it down to the Riemann sphere. And remember that if I take an endomorphism, for example, P goes to 2P on the elliptic curve, I can project it down here to P1. But now, if my elliptic curve is not isotrivial, so I know the complex structure is varying in this family, then necessarily the maps I'm getting also depend in a non-trivial way on the parameter. So non-isotriviality for the geometry of this elliptic surface corresponds to the family of dynamical systems being non-isotrivial in the sense of complex dynamics. They're not all conformally conjugate. They're not all the same dynamical system. So what does that bias? So let's see. So what's the idea? So if you have a rational point, so this is just holomorphic from here up into the surface, and then follow it with a projection down to P1, then you can iterate it. So if you start with the point P, I can look at all the multiples, 2 powers of 2 multiples here, which corresponds to just iterates over here. So for each rational point, I get a whole sequence of holomorphic maps from X down to P1. And if they're not constant, these are just covering, or branched covering maps. So I just have a sequence of branched covers from one Riemann surface down to P1.
You're doing this all relative to a particular section, so you have the...
So yes, first if you fix a P, yes, that's right. So fix one section, and then I get an entire sequence of holomorphic maps from X over to P1, branch coverage. Now the non-isotriviality guarantees that most of them are non-constant. Turns out then there would be actually a uniform bound on how many of those things could actually be constant. Okay, so now how do you get finiteness of all the torsion points? So if you look at all of the possible torsion points, it turns out then that you get a uniform bound on the degrees of these things. So torsion gives actually a uniform bound on the degrees of these projections. These are just covering maps again, from here to here, branch covers, from here to here, so they have well-defined topological degrees. As soon as you bound those degrees, then Riemann-Horowitz gives a finiteness statement, at least up to post-composition by a Northwestern transformation, which you can normalize to get rid of. So the point is that torsion gives a bound on degrees. Non-isotriviality tells us that they're non-constant, and therefore Riemann-Horowitz is just topology at the end of the day. Gives an explicit bound on how many there can be in terms of the Euler characteristic of X and the geometry of the elliptic. So the point being that we're taking the algebra of the elliptic curve, the fact that there's some group structure on the elliptic curve, and converting it into a statement about dynamics, or in this case about topology. And one other thing I wanted to point out about this slide, and this is just a sketch, there are no details here, but another thing to point out is that the reality is this statement actually had nothing to do with the elliptic curve itself. This stuff down here in the corner is really just a statement about the holomorphic maps from one Riemann surface to another, and the process of iteration. And so the conclusion of this slide, not the strategy, but the conclusion, was something that had appeared already not long ago in the literature. Matt Baker, in 2008, published a version of this finiteness. You don't have to read what all is on this slide. I just want to emphasize one thing, which is that Matt Baker contributed and actually proved this. So to emphasize his contribution, to observe that really this piece of the Mordell-Weil theorem is a consequence of a more general statement about rational functions and dynamics. Now his proof uses some analysis on the Berkovich space, the Berkovich projected line. It was a little bit technical, but it turns out that the sort of soft ingredients that I was mentioning on the previous slide give a direct and quite a bit shorter proof, which I wrote up recently just to explain the strategy. But the one thing, right, so the two things on this slide I want to emphasize without reading the details is Matt Baker's name because he worked on this, but this word right here, which is bifurcations at the bottom. And really what's going on is that we're trying to conclude a finiteness statement, in this particular case that a set of torsion points is finite. So I want to conclude a finiteness statement which has an algebraic significance, and to somehow use dynamics, some feature of the dynamical system, to extract finiteness. So this whole slide was just to illustrate that there's something about the dynamics that I can use, and in this case it has to do with the fact that the family was not isotrivial. So I'm having some type of bifurcation, and therefore I'm going to get finiteness. Okay, so just some words. I haven't given definitions, so I will try to illustrate this notion in more examples before saying something formal about it. Okay, so let me move now to the present day, or a little bit more recent. So I want to explain now a different theorem in a slightly different context, but where fundamentally the same ideas are going to give the proof. Really the same kinds of ideas. Every little piece has to be souped up a little bit. It really just boils down to the same ideas. Okay, so this is a theorem that was proved by David Massler and Mordell and Zannier. This theorem appears repeatedly in a series of articles because it was first stated in this form and then generalized. Before I read the theorem, I'll just mention that this is one instance of a long history of similar types of statements. There's a whole long history of various conjectures, and I've mentioned some of the names attached to the various conjectures and many theorems. So there's a long history that I don't have time to discuss, so this is one example from a story, from a bigger picture. But what is the theorem? So the theorem in this particular case is the following. Suppose you look at the Legendre family of elliptic curves. So here's the formula down here. So y squared is x times x minus 1 times x minus t. And I'm thinking that t is my parameter. So this is a family of complex elliptic curves here. And so my parameter, so this is smooth exactly when t is not 0, 1, or infinity. So I can think of this as a family over the triply punctured sphere. And now suppose I take two sections, or 2 points on this family of elliptic curves. Let's take these. Let's take the point with x. These are the x and y coordinates here. That's what this notation is in this equation down here. So I take the point with x coordinate 2 and the point with x coordinate 3. Strictly speaking, this is only defined up to plus or minus the y coordinate. But let's ignore that for the moment. So I take these particular points, which are chosen just because they're independent in the algebra of the elliptic curve. No multiple of this one will give a multiple of that one. Okay, so what's the statement? The conclusion is a finiteness statement that there are only finitely many parameters, finitely many t in the base, for which both pt and qt are torsion on the fiber. So only finitely many moments in this family can both of them be torsion. So that's the point. So to make this a little, I think, more comprehensible, it's worth pointing out that if you only look at one of these points, so it's possible that if you just choose a point in the family, it might be torsion for every t. But barring that, it's going to be torsion for, as long as it's not isotrivial, it's going to be torsion for infinitely many t. So if you take just one of these points, it will be torsion for infinitely many parameters. Because in any given fiber, the torsion points are dense. So in fact, if this P is moving through it in some non-trivial way, you're going to see a dense set of parameters, in fact, for which P is torsion. So P is torsion for a dense set of parameters. Q is torsion for a dense set of parameters. And so the theorem is saying that these two dense sets only intersect in finitely many points. And for this particular example, it was later proved by Stoll that in fact that intersection is empty. So they have these two dense sets, their intersection is in fact empty. Okay, so there's nothing special about 2 and 3. So one could, for example, take any old x-coordinate A and any old x-coordinate here B. As long as they're not equal to each other, the theorem goes through. And in fact, it's really much more general. It's also not just for the Legendre family, it's for any old family, as long as it's not isotrivial. And the A and B don't have to be constant in T. They can be rational functions of T, or they don't even have to be rational. They can live in some extension. They can be complex. It works in a much more general setting. The only condition you need to know is that P and Q are independent. And the independence here corresponds to this. So in the algebra on the elliptic surface, you don't want a multiple of P to be identically equal to a multiple of Q. And no matter what, you're going to get finiteness. But for now, I want to focus on the constant, the A and B case. Let's say where A and B are constant for simplicity. So by this reasoning, this thing about the torsion and the pre-periodic, the theorem on top is equivalent to a dynamical statement. And Umberto Zannier points this out in his book. He has a book on this topic. And in the introduction of his book, he emphasizes that that theorem that they prove is exactly equivalent to a dynamical statement. So here's the dynamical statement. Here is a version of the statement. Suppose, so in this example, I had the Legendre family upstairs. So downstairs, if you take multiplication by 2 on the elliptic curve, the function you get on P1 is this one. This is the quotient of multiplication by 2. When you do this projection. So suppose you take that particular family of rational functions on P1, these are degree 4 in my variable z, and suppose you fix any two numbers, A and B, you're thinking of them as points now on P1, so I fix my A and B in the base here on P1. The statement is that there are only finitely many parameters T for which both A and B are pre-periodic, or finite orbit. Because finite orbit is the same as torsion in this torsion case. So it's just a translation. It's just a direct translation of the previous theorem. And so Umberto Zannier came, after having proved this and realizing this connection, had come to us in the dynamics community and said, well, can this be generalized to other families? Or is there something else that we can do about this? Is there a dynamical proof of this statement? And so one of the things that I want to emphasize is, yes, indeed, there is a dynamical proof of this statement. And this was something that I had worked on together with Xiaogang Wang and Hesi Yi, building on some earlier work that I had done with Matt Baker. And the answer is yes, there is a dynamical proof that's using the same ideas that I presented on the earlier slides of some notion of how, something about bifurcations and non-isotriviality. There is also an arithmetic ingredient. So, okay. There's also an arithmetic ingredient, that takes place on a Berkovich space that I won't have much time to talk about, or any time to talk about. But maybe I should compare, or one of the reasons why they were asking this. So their proof of this theorem, so why get a new proof if you already have a perfectly good proof? Their proof is great, but it's very hard, at least from my point of view. It feels that there are a lot of very difficult ingredients. And one of the key things that they use in their proof, so it's all, number theory and model theory. So they rely on the result of Pila and Wilkie, a sort of point counting theorem in the context of semi-algebraic sets, I guess is the correct language. So they rely on a theorem of Pila and Wilkie, so what I consider a big tool to get their hands on this finiteness statement. So there are actually a number of sort of algebraic and number theoretic ingredients that go into their proof. And so I thought, well, since it has this dynamical statement, there might be some very directed way to get our hands on this finiteness, just using the dynamics. Okay, so let me just say a little bit about what that is. Sorry, I forgot what the next slide was. So the next slide was just to say, I won't read this, but the next slide was to say that actually the dynamical proof gives a stronger statement. So the theorem here is really about torsion points. It's very specific about when P and T become torsion points on the fibers. And there's a generalization that one can make, which is related to what's called the Bogomolov conjecture. Because the slogan is that it's the Bogomolov version of the original theorem. If you're familiar with that, then you maybe know what I'm referring to, the generalization of the Mumford conjecture for two points of small height. And so there is a corresponding generalization in this study. And the dynamical proof will give this generalization. Their proof is very particular to the fact that it was torsion points and not just points of small height. So I'm not going to say anything else about that, but I'm happy to talk about it at the end if anyone's interested. I want to talk about what the dynamical ingredients really are. And in the context of this quotient here, and the word bifurcations, which appears twice on this slide. So you'll see the word bifurcations here, and you'll see the word bifurcation here. So this was, again, just to remind you the statement of the theorem. I have 2 points, and in the Legendre coordinates, that the elliptic curve ET was the set of solutions to this equation. And these are the x and y coordinates of a given point, a given solution. So you're supposed to take these points, and tor A and tor B correspond to the set of parameters for which tor A is the set of parameters for which P is torsion on the fiber. Okay, so the first observation, this is actually, it's an if and only if statement. That this intersection of parameters where they're both torsion is infinite if and only if they're actually the same point. That's really the statement. It's an if and only if statement. Now you get an infinite intersection if and only if they're exactly the same point, in which case, of course, those two sets are actually equal. So how would you go in one direction? This is supposed to be the easy direction. There's a number of theoretic proof of this, but there's also actually a complex dynamics proof. So step one to do what we think of as the easy direction of this is really just relying on some classical ideas in complex dynamics, in particular Montel's theorem, to show that, well, if this point is not torsion for all t, then that point is somehow bifurcating for this family. It's sometimes going to be preperiodic and it's sometimes not. And one can use a very standard argument using Montel's theorem about normal families for holomorphic functions, normal families of holomorphic functions, I should say, to deduce that this set has to be infinite. And then the second ingredient is an equidistribution theorem, which I will illustrate on the following slides by pictures. But the idea is that for any one of these points, if you look at that set of parameters, it will be distributed according to some natural measure on the base. So the base for this example, remember, was this triply punctured sphere. It was a P1 minus 3 points. And this set of parameters where P is torsion has some natural associated distribution. And it's if you take not only the entire set, but any sequence of subsets which are Galois invariant, they're going to uniformly distribute with respect to some natural measure, which depends on the point you start with. And then the last ingredient, so this piece we have to use a theorem that was proved by a series of authors about 10 years ago now, independently. They all were working on it at the same time. And this is the piece that actually takes place in the Berkovich space, and I won't talk about the proof at all. But the last piece is a study of what we call the bifurcation measure. So this measure really is, if a point were a critical point for a family, this really would be what we call a bifurcation measure in complex dynamics. But here we can use complex analysis to prove that the two measures are the same if and only if the points are same. So just the only thing I want to say here is that ingredient steps 1 and 3 are really complex analysis or complex dynamics methods. And step 2 is the one that involves some arithmetic geometry ingredient, non-Archimedean analysis in this particular case. Laplacians on the Berkovich. Okay, so I just want to show a picture to illustrate what I'm talking about equidistribution. So the next, I was going to say what the hardest part is, but let's ignore that for now. Just to illustrate what kind of equidistribution I mean. So these slides here are what? So these yellow dots are supposed to show, so I'm given this particular family of elliptic curves, and I've given a point P, so I've given a point P, which on the elliptic curve was, so in its x and y coordinates, the x coordinate is A. And then it's whatever the y coordinate is, so that it satisfies this equation. Plus or minus the square root of that expression. Okay, so for a equaling 2, I'm plotting some dots here, and some of them are huge and some of them are small. Let me turn the lights off so you can see the picture slightly better. The size of the dot is related to the order of the torsion. I was using dynamics to draw the picture, and so the size of the dot is actually related to something slightly different. But roughly speaking, the size of the dot corresponds to a lower order. And I'm plotting the t values for which my desired point is torsion of order either 2 or order 4 or order 8. So a power of 2 up to n equals 3. And those are the dots you get. So you plot a picture, and this is the scale. These are the t values that I'm looking at. And you just get some collection of finitely many dots corresponding to those are the parameters where p has that order of torsion. So this giant dot corresponds to a lower order of torsion. But if you increase the order of torsion, you get more and more dots. I'm increasing the number of dots. I'm finding more and more solutions to the corresponding algebraic equations when these things become torsion of that order. So here, as I increase the order of torsion, notice that I have a whole lot more dots. Remember that if I look at all the parameters t, my entire picture is going to be yellow. This is going to be a dense set. And you can start to see the elliptic curve structure in the structure of these dots. You see the grid pattern coming from when you have, say you look at the elliptic curve and its sort of uniformized parameters, you see modulo lattice, the torsion points are in a grid structure, and this is what the grid pattern that you're actually seeing in this picture. As I increase the order of torsion, I get more and more and more dots, and as I said, they're dense, so it's just going to fill out the picture. But what I want to emphasize is the corresponding distribution. These are distributing themselves in a very particular way, as according to some measure, which of course depends on the input data, the geometry of the elliptic curve, and the point I start with. If I change that point, I get a different picture. I get a different collection of yellow dots. So here, I have one point here, I have these yellow dots, here I have these yellow dots for two different starting points. But a priori, the distributions could be the same. They're both dense sets of yellow dots. And what the theorem says, again, is that this distribution is the same as this if and only if they were actually the same point. But not only that, so we can prove that, that they're different distributions, but they're different points. But you also get that the yellow dots only intersect at most finitely many. Of course, my yellow dots are huge, so of course they're overlapping. But if you had infinitesimal sized dots, they would only coincide if the distributions were actually the same. So you have at most finitely many yellow dots. And also in this case, for a equals 5 and a equals 2, it's an empty intersection. Okay, so that was the statement at the bottom here. So these distributions that we're getting, what are called bifurcation measures. So they're related again to some family of dynamical systems, the particular one that I showed on the previous slide, and some notion of bifurcation. How the point A or the point B is somehow passing through the Julia sets of these dynamical systems. Okay. Let me skip this for now. I want to give another illustration in a slightly different context. So those pictures and that proof were very much inspired by something that's really well known in the study of complex dynamical systems. So let me now give an illustration, a completely analogous equidistribution illustration in a much more well-studied family of dynamical systems from the point of dynamics. Okay, so here, this is the famous quadratic polynomial family, which when someone's learning dynamics in dimension 1 or complex dynamics, this would be the first family that you would look at. So let me do the analogous construction here, and hopefully you'll see something very familiar. So this is the family, I'm calling my parameter C now, not T, because this is the notation we usually use in complex dynamics. So the family is this family of quadratic polynomials. Okay, this is how it depends on C, so the parameter space is the complex plane. And suppose I do exactly the same construction with the point A equaling 0. So in other words, I want to find the parameters for which that point has finite orbit. Or in particular, I'm actually going to draw the set of parameters for which 0 comes back to itself. It's actually periodic. So if you start plotting, so what is this? Is just some algebraic equation. So if I'm looking at the nth iterate of this quadratic polynomial evaluated at 0, and I want it to loop back to itself, so this is some polynomial equation in C of degree 2 to the n minus 1. So this is just some polynomial equation in C, and I'm looking for all the solutions. And that's what I'm plotting. And that's exactly the same thing I was doing, by the way, in the previous one, just for the other family of dynamical systems. So for n equals 1, this is just the equation C equals 0, and there's the dot. at c equals 0. And for n equals 2, this is this polynomial equation, because c squared, if you plug in c squared plus c, that's what you get for the second iterate of 0. It's this equation, which has, of course, two roots at 0 and at minus 1. But as you increase n, my dots are getting smaller because of the way I'm drawing the picture. But you see that there are exactly 3 more dots that have just appeared. And now I have an equation of degree 4. And as n grows, we're going to get more and more dots. You can't quite make out all the dots. There's actually another little dot down there. But as n grows, you get more and more dots. Now, one thing that's different in this setting from the previous setting is that all of the yellow dots are actually contained in this picture. So it's not hard to prove for this context that all of the solutions to this particular collection of polynomials have to lie in the rectangle that I've drawn. It's not going to be a dense set of points like it was for the torsion points on the elliptic curve. And as n increases, hopefully now this is a familiar picture. I know it's familiar, at least to all the people who are in the room who study complex dynamics, but maybe also to the prospective students who are here for the lecture. This is what's called the Mandelbrot set. These yellow dots that I'm plotting are actually accumulating everywhere on the boundary of the Mandelbrot set. Now, what is the Mandelbrot set? So in this family, the Mandelbrot set is this famous set that we still don't fully understand, which consists of all the parameters C. So by definition, it's the set of all parameters C for which the orbit of 0 is bounded under iteration. So this orbit of 0 here is bounded. So of course, if 0 comes back to itself, the orbit is bounded. It's a finite set. But the Mandelbrot set, which is everything here in dark, it's supposed to be everything in black, but you can't quite make out because it's so make it all out because it's very, very thin, corresponds to all the parameters for which 0 is bounded under iteration. And these yellow dots, it turns out, are accumulating everywhere on the boundary of the Mandelbrot set. So you take the closure of the entire set of yellow dots, and it contains the whole boundary. But not only is it equal topologically to the whole boundary, it's in fact, these dots are uniformly distributed. As n increases, these dots are uniformly distributed with respect to a very natural measure on this object, which in this case turns out to be the harmonic measure. This was proved by Levin in the 1980s, around that year, that we just observed that if you order them by the period here, then these dots, you put an equal mass on each of these dots and let n go to infinity and normalize it, then the limiting distribution is precisely the harmonic measure, that is to say, relative to the domain, the complementary domain, relative to infinity. So that the probability of sort of Brownian motion going from infinity to hit the boundary. Where are you going to hit on the boundary of this Mandelbrot set? And that's the distribution that you see. It plays a very important role also from a dynamical point of view. And this is where the bifurcations terminology is really coming from. In this context, in this family, that support of that measure, which is the boundary of the Mandelbrot set, is precisely what we call the bifurcation locus for this family. If you look at the dynamics of this family, as C varies, if you're moving around inside the interior, then the dynamics are stable, which means that those Julia sets, which I haven't defined, are all looking the same. They're all topologically the same. But if you take your C and you push it outside or through the boundary of the Mandelbrot set, then the dynamics will change in a dramatic way, and the maps are no longer topologically conjugate on the Julia sets. The Julia sets are not going to be homeomorphic. And if you pass outside the Mandelbrot set, the Julia sets are counter sets, and inside they're all connected. So the boundary is what's called the bifurcation locus, and this measure is what's called the bifurcation measure. And the corresponding thing for elliptic curves is really just an analogous object to this. And you could do the same kind of construction for any family of maps or for any starting point. This case, it plays a very important role. 0 is special here because 0 is the critical point. And that's what's particular, why the 0 is so important, and why the Mandelbrot set is defined in terms of the orbit of 0, because it's the critical point. But from the arithmetic point of view, for these algebraic types of questions, one could just as easily do the same thing for another point. So if you did exactly the same thing, you wanted to say, suppose I have the starting point -1, and I just simply plot all the yellow dots where -1 becomes periodic, all the parameters where -1 becomes periodic, those yellow dots are going to accumulate everywhere on some other shape in the plane, and that'll be this one. And that's the picture you get. The boundary of this black thing is precisely the accumulation set for all of these yellow dots. And the harmonic measure on the boundary of this thing is the distribution that you get from the limiting distribution of these yellow dots. Okay, so for exactly the same reason as I mentioned in the elliptic curve setting, one can prove corresponding dynamical statements, so statements about complex dynamics that don't have an obvious sort of arithmetic, well, what should I say? There's no direct connection to the arithmetics, but the same ingredient can be used to prove a statement of this sort, which is just fun, so let me just mention it. For example, if you take this family of quadratic polynomials and you take any 2 points in the plane, A and B, as long as you assume they don't have the same square, then there are only finitely many complex parameters C for which they're both of finite orbit, so that they're both eventually periodic under iteration. Only finitely many parameters for which they both become periodic. This is exactly the same statement as the Masser and Zannier statement, and that was about elliptic curves and torsion points. This is about some other family of dynamical systems. It's the same statement, but just in a different context. And just to put a little bit more context, I mean, by contrast, there can be infinitely many parameters for which they're both in the Julius set. So it's really something very particular about having finite orbit, not just being bounded or being in the Julius set. But the proof argument that I sketched in the case of elliptic curves is actually really the same in here. The strategy of proof is really the same. And the proof shows, I said here, that finiteness can be detected experimentally, can be detected completely by just drawing the picture. The fact that the Mandelbrot set, which was 2 slides ago, is not the same set as this, what I called a Mandelbrot-like set, some other funny fractal thing. The fact that the sets are different implies that, of course, those distributions are different, and therefore these infinite sets of yellow dots have only finite intersection. The infinite sets of yellow dots have only finite intersection, which I have to say is not obvious from the picture, in the sense that if you look in this very special case, both of these sets include C equals -1, and they also seem to include much of this circle around -1. In this case, we have this nice circle around -1, which is included here in the boundary of the Mandelbrot set. And in the other set, we have something that looks very much like the circle. Although if you zoom in, you'll see it's not actually equal to the circle. It has some weird fractal structure. So what's not completely obvious is that all the yellow dots that are accumulating here are really genuinely different from all the yellow dots that accumulated here. That you can't check experimentally, but you can see that the whole picture on a large scale is different. And that's enough to know that the intersection is finite. And that's what the proof shows. Again, that's something about bifurcation, something about the big picture is showing, is you'll be able to deduce finites from that. So just a few minutes left. So let me switch gears just a little. In the same context, inspired by these various results. So for example, the work of Masser and Zannier, as well as all those conjectures that I mentioned on the previous slide, this long history of results, they all fall under an umbrella, which is referred to as unlikely intersections in arithmetic geometry in various contexts. So Matt Baker and I were inspired to look at something that has a more intrinsic dynamical flavor, a version of those theorems that could be formulated in the context of complex dynamics. So as one definition that I'd like to write on the board in the last few minutes to make this slide make sense, let me turn that light back on. So we just write one definition on the board, the MD, which appears on the top of that slide there. So MD here is representing a moduli space of rational functions. So here we're looking at maps, so rational functions. So this is the Riemann sphere to the Riemann sphere. And if I specify that it has degree D, and I want to assume that D is at least equal to 2, but modulo an equivalence relation, that's why it's a moduli space, and the natural equivalence relation on this set of maps is conformal conjugacy. So F is equivalent to a map G if and only if there exists a Mobius transformation, so that F is conjugate to G by this Mobius transformation. So A here is an automorphism, like a Riemann sphere. So A is a Mobius transformation. So this is the natural equivalence relation. And this space has some very nice structure. It's a complex affine variety. Its complex dimension happens to be equal to 2D minus 2, which you might recognize as the number, which is equal to the number of critical points of any element in this space. So F being a holomorphic map from P1 to P1 of degree D by Riemann-Hurwitz has exactly 2D minus 2 critical points. Okay, so this is relevant because that's the dimension of moduli space. So now let me formulate this. If you're familiar with the Andre-Oort conjecture from arithmetic geometry, you will recognize that I've just stolen their slogan and replaced it with the main object with MD. I've replaced the word Shimura variety with the symbol MD. So the statement is, conjecturally, we believe the following is true. That a subvariety of this moduli space, some algebraic subvariety of this moduli space, has a Zariski dense set of special points within it, if and only if the subvariety is special. So this has no meaning without understanding what I mean by special, but that's just the slogan from the Andre-Oort conjecture, which is why I wrote it that way. So what does special mean? So in complex dynamics, so there's a certain kind of map called a post-critically finite map. One of these, an element in here, is post-critically finite. If you take a representative, if each of its 2D minus 2 critical points has a finite orbit. So post-critically finite means that everywhere the derivative vanishes, if you follow the orbit of that point, its orbit will be finite. And those post-critically finite maps play a very important role in our understanding of this moduli space, of dynamics, of bifurcations, of a lot of things. So I'm calling those special points. Special, again, it's just stolen from other context, but I'm just going to call them special points because they really are special from a dynamical point of view. Now, special variety here corresponds to subvarieties that are defined by critical orbit relations. So just to give you an example of what I mean, so a critical orbit relation would be something of the following sort. A subvariety of this moduli space, which is defined by an orbit condition on the critical points. So suppose Ci and Cj are two of the 2D minus 2 critical points. If I force that their grand orbits coincide, or in other words, that some iterate of one coincides with some iterate of the other, that would be an example of an orbit relation. And that equation cuts out some hypersurface inside this moduli space. And so special varieties are ones that are defined or cut out by such orbit relations. And we believe that you can only have lots and lots of special points if, on some subvariety, if the variety is itself special. And just as a concrete example, so if you start out with something that's defined by critical orbit relations, it turns out it's not too hard to prove that it always has lots and lots of special points. And so a special curve, for example, in dimension 1, will always, Zariski dense will correspond to infinite. So a special curve will always have infinite special points. And here's an example of one. I'm using some terminology from a paper of Milner called SP. So in the space of cubic space, there's a curve consisting of degree 3 polynomials where one of the critical points is forced to be fixed throughout the curve. Then I just plotted some yellow dots, and you can see that they're, in fact, sort of a copy of the Mandelbrot set here, and you actually have infinitely many yellow dots in this picture. So anytime you start with a special variety, you will always have lots and lots of special points in it. But it turns out sort of the converse direction is actually is more challenging. That's really the main goal in this conjecture, is to understand that if you're just handed a curve, maybe it has some special points. This is another sort of terminology from one of Milner's papers. You take the slice of degree 3 polynomials for which it has a fixed point of multiplier 6. It's just an example. We know that there exists at least one yellow dot on that curve, but this curve is not defined by critical orbit relations, one can prove, and then it turns out that in fact there are only finitely many yellow dots on that curve. And for the dynamics people in the audience, let me just mention that the general statement, at least for these Pier 1 lambda curves, is that, just to say the statement, is that Pier 1 lambda contains infinitely many post-critically finite maps if and only if lambda is 0. So that's the theorem in that context, just for those who know what those objects are. So just to say, it's of course a lot harder to show something is special. And so here I want to conclude with a statement of a theorem of a special case of this conjecture. So this conjecture is for the most part wide open, and there are only certain settings we can solve, such as, for example, for the dynamics people at least, curves of the form P1 lambda in the space of quadratic rational maps or cubic polynomials. Recently, for cubic polynomials, it was just proved for pure n lambda. Anyway, so there are only very special classes or things of this sort. And Holly Krieger is going to speak in the dynamics seminar tomorrow and explain some other cases that have to know that she's going to do. So this is an announcement for that talk tomorrow. But anyway, so just to illustrate one of the theorems that Matt Baker and I were able to prove for curves, rational curves of polynomials inside these moduli spaces. So it's really a very special class of curves. But this theorem, I think, illustrates sort of what kind of result we expect will be true in general. The statement is if you take one of these particular curves that consists just of polynomials now, and I want it to be a rational curve, and that is parameterized by P1, and with a particular formulas, then the statement is that there are infinitely many special points. That is, there are infinitely many post-critically finite polynomials in this family, if and only if the critical points satisfy very strong critical orbit, very strong relations. There's a critical orbit relation between any pair of active critical points. So if I erase this H, this is a critical orbit relation in the traditional dynamical sense. The nth iterate of one critical point coincides with the nth iterate of another. The H is a symmetry. So there are examples where the whole family of maps could have a symmetry. And it turns out that those are the only kinds of, it's also a polynomial itself. So F, some iterate of F has to commute with H, which is also a very special and already classified list of things. So we completely understand the kinds of symmetries, we completely understand what kinds of special curves we could have in this case. And the point is just simply that the proof is basically the same. The ingredients that go into the proof are, again, some combination of traditional complex dynamics and complex analysis together with some sort of equidistribution theorem. And in this case, to get our hands on the explicit formula, there had to be more ingredients. And in this particular case, we can rely on Ritt's work from the 1920s about the decomposition theory for polynomials. So I think I'm out of time. So let me just, this was a slide that I had skipped previously. It has the formal statement of the conjecture, so at least those of you who are in the field might want to see the way the conjecture is actually formulated, and that's this here. So I think I better stop.
Questions?
So you have explained to us that sort of arithmetic of elliptic curves is a little tiny part of dynamics.
That's exactly right.
So how about high genus? So is dynamics of any use in the
higher dimensions, like for a million varieties?
High genus curves. If you take high genus curve, is there any relevance to the?
But is there any dynamics on a higher genus curve?
No.
So.
No, and that's why the question.
Yeah, but no, I mean, I don't know. I mean, in terms of studying the arithmetic, I don't know. But yeah, because we don't have a dynamics theory in that case. So yeah, but of course, if you're projecting it down to P1, maybe there's some way to explain. But I actually have no idea. So I actually have no idea.
Could be some correspondences instead of dynamics of a one map, it would be dynamics of.
That's right, which are defined by some, and I just don't know.
So genus 2 curves, for example, are all hyperelliptic.
Are all hyperelliptic, and of course, yes, have their projections to P1, but I don't know if there's any way to explain that in this case, to understand.
Okay, so Laura is giving a mini course next week
Starting next week.
on this subject, so if you're interested. Okay, let's end this.